Curvatio, low-cost measurement system for spinal curvature. So Martin, the floor is yours.
Thank you, Giuseppe. Well, first of all, thanks everybody for being here, for the time. It's going to be a little compressed on time, but I'll try to make it in the 12 minutes as suggested. If at any point I'm talking too fast or the audio is bad, usual virtual stuff, just let me know. So the work, as mentioned, is called Curvatio, a low-cost measurement system for spinal curvature. And just a little overview on how this presentation is going to happen. I'm going to briefly show you guys a video on what the project is about. And the idea is just to give a big picture, because I think it then makes it easier later during the presentation to connect the little bits and pieces together with the whole context. I think it's easier to follow in that case. After the little trailer, I'm going to sort of start from the actual beginning and present what was the motivation for the project. Then go into the details of design and implementation, how we validated our prototype, and then close off with a few thoughts and comments. Right. So as I mentioned, the first thing is just a little trailer. So what is Curvatio? Curvatio is a little device. You see here our prototype that you connect via USB to your computer. And that allows you to essentially, in real time, make a measurement or an assessment of a patient's spinal curvature in both the sagittal and the coronal planes, so front and side, essentially. Once you have collected the measurement, which you see in real time, you can actually extract information out of this measurement. And within the same software tool and within this, using the same device, you can also make goniometer measurements, so angular measurements and range of motion measurements. So this is just for really quick overview on what the project is. And as I mentioned, I'm going to actually now start from the beginning with the question, okay, what was our motivation to start this project after all? Well, we in our research group were interested in postural assessment. So basically measuring certain lengths and angles and ranges of motion of the human body, because being able to do that properly allows you to identify or diagnose potential deviations in a patient's posture, but also in the process of the rehabilitation of said deviations, evaluate if there is improvement or not in a more objective manner. And there are many ways that you can do postural assessment, and we're going to sort of rank them in a very simplistic way here in sort of this axis of cost / invasiveness / accuracy, because although they are different measures, they're somewhat tied. So in the leftmost part of the spectrum, you would have something like a goniometer, which is basically just a manual ruler that a professional needs to, well, use on the patient to extract measurements. Requires, of course, that the professional does it correctly. And on the other end of the spectrum, sort of like the ground truth, the golden truth, you have tomography, MRI, X-ray, which will give you then an exact measure of patients' postures or certain reference points that you want. And of course, this works perfectly, except that you are subjecting the patient to radiation, which is optimal, and there's a bit of a cost associated. And for particular things like ranges of motion, well, if you've ever been inside of an MRI machine, you know that there's not a whole lot of wiggle room in there to do range of motion, right? Somewhere to the left of the spectrum, again, you have something like photogrammetry. So you take images, markers, you can extract information out of that, but that still requires you to, well, identify the markers, check the images. And in this spectrum, there was this one product we stumbled upon that for our group was particularly interesting, which is called the spinal mouse. And the spinal mouse is essentially a tool with which you can measure, using a wheel and some angular sensors, the spinal posture of a patient. And this aligned very well with our goals. So we looked at this product and we asked ourselves, in particular, at the features and at the price of the product, and we asked ourselves, okay, how can we improve? And so we came up with a little list of little targets we set in ways that we could improve on this existing project and come up with an idea that was somewhat better. And there were a few goals set here. So basically, we knew that we wanted to acquire both linear and angular positions. We set a few ranges and resolutions. And we had other non-functional requirements, like it being inexpensive, which is, of course, for a developing country like Brazil, where this was being developed, a big point. Be able to do cervical assessment and allow also for real-time visualization of the data being collected. And this is this goal setting is actually the first step in design methodology that we are following. So the PAL invites the well-known design methodology, and you see in the corner there, this was essentially the first step in that informational phase. We moved on then to the next phase, the conceptual phase, where we were thinking, okay, we have these requirements. Let's think about what are the elements in the system that can actually solve that problem. And so we see here a very rough sort of conceptual signal flow of the product. On the leftmost, you have the patient and its spine. You would have, of course, some sort of measurement wheel, whose movement gets translated into some sort of digital information via an encoder. The angular measurement then happens with an inertial measurement unit, or an IMU, which is essentially an accelerometer and a gyroscope together. Those are crunched, these numbers are crunched by some sort of inexpensive microcontroller. We actually did use an Arduino in this project. And these then get transmitted to a computer that does the heavy lifting. So the next step is then, well, we identified the players, the signal flow. Let's put it all together in this embodiment phase. And the embodiment phase, as you see here, this was our very first prototype. We essentially just rammed everything together with a 3D printed shell, again, thinking about flexibility and cost effectiveness. You see there the microcontroller, the encoder attached to the measurement wheel, our IMU that does the angular measurement, and a little status LED and user button for the interaction. Okay, now we have a device physically, but our next step is, of course, to extract data out of it. We want to be able to measure the patient's posture. In this concrete case, it's spinal posture, right? So how do we do that? So essentially, we are talking about with the device, which I actually happen to have here, there, the camera. We want to measure a couple angles. We want to measure basically its pitch angle and a roll angle, so around this. And you see here, identify them with psi and theta, essentially. And then we, on the left image here, you see some frames of reference that we defined. Our main interest as a frame of reference is frame D, which is the point that touches the patient's back. And of course, we have a frame of reference, which is the IMUs, or the inertial measurement units frame of reference. And they're placed in such a way that translating the measurements of one to the other is trivial. So having that in mind, how did we proceed? We essentially, like I said, want to, in the first step, identify what are the pitch and roll angles of the device, standing upright, going down the patient's back. We start this by essentially taking estimates that use only our accelerometer as an input. So we basically do a little arctangent that just computes, okay, where is the gravitational pull? How is the gravitational pull oriented in relationship to the accelerometer's frame of reference? This is our first estimation. And the second estimation uses the gyroscope. And we're basically saying, right, the gyroscope gives us angular velocity. So we're essentially integrating this angular velocity to get angular position. And then we have our second estimate. We combine these two estimates then via a very simple method, which is called a complementary filter. And a complementary filter, as you see, is easy to implement, which is compliant or goes well with our little microcontroller we were using. And it essentially exploits the fact that our gyroscope has a high pass behavior, so it's actually a derivative of a signal, whereas our accelerometer is just like a low pass system. So in steady state, we'll converge to the measurement of the accelerometer, but the dynamical, the transients pull in the data from the gyroscope. So it works because the systems have those characteristics. Once we then have a sort of quality or decent pitch and roll angle estimation, the next question is, right, we are moving this guy vertically, so we're going down the patient's back. How do we actually reconstruct this trajectory? That is, if I am in a point P of K minus 1 in an instant, how do I find my next point P of K? And what we're doing here is essentially saying, right, here on the rightmost part of the equation, I essentially have a vector that starts off oriented vertically in the z direction. And this is the length of the displacement of the wheel. You see there the difference between the encoder pulses, d of k and d of k minus 1. A constant, which is essentially the radius of the wheel, and two rotational matrices for my pitch and roll. So we combine everything together and we can sort of stitch the little segments of the trajectory. Great. Now the question is, does it work, right? And to reply that, we constructed a little testing jig, which supposedly doesn't look necessarily like a human back, but it does contain the overall appearance of what this project or the product would be doing. And we then took our little prototype, attached a lot of optical markers to it, got an OptiTrack, which is a validated device with a known precision, and said, okay, let's see if the measurements actually match up, what we measure with the device and what the OptiTrack tells us. And those are the results. So you see, we have here just the graph for one run. We actually took 30 measurements in the paper. And you see in blue, you have the OptiTrack's trajectory, so what the OptiTrack saw. In red, the prototype, and in green on the side, the error. And you see that they actually follow along quite well. And you see here on the left, let me actually just drag the cameras from everybody. Right. The error that we accumulated for the two planes is on the sagittal plane, a linear error of 4.5 millimeters and 3.9 for the coronal plane. And the root mean square error was 27.5 on the one plane and 25 millimeters on the other. So considering how everything is fairly rudimentary, we were quite satisfied with the results there. So did we improve? So now let's go back to the beginning and ask ourselves, did we improve? For the first thing we were looking, so acquiring linear positioning, we achieved the 2 millimeter resolution we were talking about. And this you can see via the encoder resolution, wheel size, and whatnot. We did not, however, go over the 0 to 1.5 meter range. So this is open, but of course it looks very like it would actually do it. Acquiring angular position is covered. We do have this complete 0 to 360 capability with the 1 degree resolution. Inexpensive. The entire thing did cost under $100 to assemble. Cervical assessment is doable, would require, of course, a correct protocol to do so. So we sort of get a gray tick. And real-time visualization, as you guys saw in the video, is covered. So to close it off, what now? As you guys seen, we continue developing the product or project. It actually looks a bit different right now. It has a bit of a cleaner view. It is not 3D printed, but laser cut, which does give it a bit more robustness. The software is also improved, but there is, of course, a few other things that still need to be worked on, like the gray ticks in the previous slide, and other ideas that are always coming around. So that was a speed run, but I'm done, and I appreciate your attention. So if there are any questions, please.
Thank you very much, Martin, for this very nice presentation and for sticking at the time. The paper is now open for discussion. Is there any question from the audience?
Yeah, if I may, Juan Antonio Carretero here.
Please, Juan Antonio.
Yeah, just a quick question. What is limiting your range from 0 to, I think, 1200 or 1500 you were looking at? Mm-hmm. It seems to me as though you're using a potentiometer, aren't you? Mm-hmm. So is that what's limiting it?
No, so the 0 to 1.5 meters was, I think, sort of this arbitrary benchmark. Can we do this? Because if you're measuring a patient's back, it's unlikely that it's going to be more than 1.5 meters. So we just took it as a goal, sort of arbitrary, like I mentioned. But the angular, the displacement of the wheel is measured with an encoder. And the encoder has then no limitation. It can just rotate forever. And so there should be basically no issue in reaching the 1,500 millimeter range that we put in there. The only reason I gave it a gray tick is because if you really want to be tight about this, that's not covered in the paper, so I can't claim that it was tested. So.
Ah, okay, I see. So there is no limitation.
No.
So the way you showed it, it seems as though did the encoder actually look at the one you showed on the picture? Because that's
it actually did in that first prototype.
Okay.
I don't think you can see it in the picture, but we did use that Burns encoder that I showed there. In this particular picture, the image is taken directly from above, but it is indeed that little component there, that guy there in the middle.
No, it seemed to me it looked more like a potentiometer, not so much as an encoder.
Right, that guy is an encoder. And in this new version we developed, it's not an encoder anymore. It is actually a magnetic encoder, or it's still an encoder, but it's a magnet that rotates, and we have a magnetic field measurement in there.
And as I see your new prototype, the wheel is made, doesn't have the serrated figure. So you're not concerned of it not slipping. So I'm guessing that your patient is always has the back, a naked back, so that it would not slip?
This is a good question, and we ran a few tests with it, both on the naked back or also in clothing, and we never really saw slippage happening. I won't tell you that we have proper measurements of friction coefficients of stuff or stuff like that. We don't. But on a sort of like person by person basis, we didn't have any problems. But we were discussing at some point actually coating the wheel in a more rubbery sort of surface, because this was a concern that was raised.
You could make a groove and just put an O-ring.
Correct. That was an idea, but these parts are laser cut, so making a groove would probably require milling it, which then again is sort of like a cost constraint. So we didn't. And the thing that is somewhat useful in here is that you can look through it, so you have a better sort of view of what you're doing at the moment you're taking the measurement, which we also thought about.
All right. Thank you.
Thanks.